Leibnitz theorem. State and prove the Leibniz theorem for the nth derivative of the product of the two functions n is greater than 1. Solution statement: if u and v are the two functions of x having derivatives of the nth order, then u v nth u v n u n v plus nc1 u n minus 1 v1 plus nc2 u n minus 2 v2 plus so on. ncr un minus r vr plus so on plus ncn u v n, where the suffix u v u and v denotes the differentiations with respect to x. Proof: we shall prove the theorem by the mathematical induction. Step 1. Putting n equals to 1, the above statement becomes uv1 equals to u1v plus 1c1 uv1, or uv1 plus u1v equals to u1v plus v uv1, because uv1 equals to u dv over dx plus v du over dx equals to u v1 plus v u1. Now, which is true, hence the theorem is true for n equals to 1. Step 2. Let the theorem be true for n equals to m. Say that is uvm equals to umv plus mc1 um minus 1 v1 plus mc2 um minus 2 v2 plus so on plus mcr um minus r vr plus so on plus mcm uvm. Step 3. To prove pm plus 1 is true. Now, differentiating both sides with respect to x, we get uvm plus 1 equals to um plus 1 v plus um v1 plus mc1 into um v1 plus um minus 1 v2 plus mc2 into um minus 1 v2 plus um minus 2 v3 plus so on plus mcr into um minus r plus 1 vr plus um minus r vr minus 1 plus so on plus mcm into u1 vm plus u vm plus 1 equals to um plus 1 v plus 1 plus mc1 into um v1 plus mc1 plus mc2 into um minus 1 v2 plus so on plus mcr plus mcr plus 1 into ur plus 1 vm v minus r vm minus r plus so on plus mcm uvm plus 1 equals to um plus 1 v plus MC0 plus MC1 into UMV1 plus MC1 plus MC2 into UM-1V2 plus so on plus MCR plus MCR plus 1 into UM-R VR plus 1 plus so on plus MCM UVM plus 1 equals to UM plus 1V plus M plus 1 C1 UMV1 plus MC plus 1 C2 UM-1 V2 plus so on plus M plus 1 CR plus 1 UM-R VR plus 1 plus so on plus M plus 1 CM plus UV M plus 1, because 1 equals to MC0 and MCM plus 1 equals to MCM plus 1 MCM plus 1. Also NCR plus NCR plus 1 equals to N plus 1 CR plus 1 for all R equals to 0, 1, 2 and so on, which is exactly the same form as the given by the formula. If you put n equals to m plus 1, this shows that the theorem is true for n equals to m plus 1 whenever is true for n equals to m, but the theorem is true for n equals to 1 proved above. So by the principle of mathematical induction, the theorem is true for every integer n.